Chemical reactions always happen according to the mole ratio, and this mole ratio is defined by the coefficients in the balanced chemical equation. But when we combine chemicals in real life in a reaction mixture, it's almost never that those chemicals are present in that perfect mole ratio. For example, let's look at the reaction below, where we have hydrogen gas combining with oxygen gas to form water. The mole ratio says that 2 moles of hydrogen need to combine with 1 mole of oxygen to produce 2 moles of water. But in our reaction mixture, we have 1 mole of hydrogen, and we're mixing it with 3 moles of oxygen. Since the reaction mole ratio is a 2 hydrogen to 1 oxygen ratio, that means that when I use up all 1 mole of my hydrogen gas, I'll only have used up half of a mole of oxygen gas. And the reaction is going to stop at that point because I will have no more hydrogen gas, even though I still have 2.5 moles of oxygen gas. The reaction does form water in the process, and a 2 to 2 mole ratio of hydrogen to water is the same as a 1 to 1 mole ratio. So for every mole of hydrogen consumed in the reaction, we'll produce 1 mole of water in the reaction. So the change during the reaction is we're going to gain 1 mole of water, and since we had no water to start, that means that after the reaction we're going to have 1 mole. This table that I'm filling in here is called a BCA table, or a BCA mole table, which allows you to organize the moles of substance present before the reaction, the change that occurs during the reaction in moles, and then the amount of each substance after the reaction in moles. Every real reaction will be limited by whichever reactant runs out first. This is called the limiting reactant. It is the reactant that is completely consumed in reaction, and then the reaction stops once that reactant has been used up. In this process that we just showed, hydrogen gas is the limiting reactant. And we could see that easily with the BCA table and also the amount of moles present at the start. But it's not always that easy to see. So let's talk about how we can determine which of the reactants is the limiting reactant. To determine the limiting reactant, you start with the amount of the first reactant you have, and then you figure out how much of the second reactant would be required to completely consume the first. So in the case of the reaction above, we started out with 1 mole of hydrogen gas. And according to the balanced chemical equation, for every 2 moles of hydrogen gas in the reaction, we need 1 mole of oxygen gas. So this means that it would require 0.5 moles of oxygen gas to completely consume the hydrogen. Since we have more than enough O2 with our 3.0 moles present at the start, that means that hydrogen gas is our limiting reactant. If we did not have enough O2 to consume the H2, then oxygen would be our limiting reactant. The theoretical yield is what we call the amount of product that should be formed in a reaction. And since the limiting reactant controls when the reaction stops, the limiting reactant determines the theoretical yield of a reaction. Let's calculate the theoretical yield of water in this reaction. We'll do this by starting with our amount of limiting reactant, 1.0 moles of hydrogen gas, and then using the mole ratio from the balanced chemical equation of 2 moles of hydrogen gas consumed for every 2 moles of water produced. We're going to see that 2 to 2 reduces down to 1 to 1, so we're going to form 1 mole of water in the reaction. This is the same change that we saw happen in the BCA table, it's just showing it in a dimensional analysis form. The excess reactant is the reactant that remains left over after the reaction has stopped. This reactant cannot react further because there's no more the limiting reactant to combine with or to react with. In the reaction above, oxygen gas was our excess reactant. Now let's calculate the moles of excess reactant left over after the reaction using dimensional analysis. We already did this on the prior page with the BCA table, but let me show you the dimensional analysis work. We're going to start with 1.0 mole of hydrogen gas, which is our limiting reactant, and then we're going to use the mole ratio from the balanced chemical equation of the fact that it's going to be 2 moles of hydrogen gas consumed for every 1 mole of oxygen gas used. This is going to tell us that we're going to need 0.5 moles of oxygen gas to completely consume our hydrogen gas limiting reactant. Next, we just have to find out how much will remain. Well, if we started with 3.0 moles of oxygen gas prior to the reaction, and then we use 0.5 moles of oxygen gas in the reaction, we will have 2.5 moles of oxygen gas after the reaction has stopped. Okay, let's practice figuring out what is the limiting reactant in a reaction mixture. So for example, we're going to deal with this reaction where we're going to use household lighters which use butane, and they combust with oxygen and air to form carbon dioxide and water in a typical combustion reaction. We provided you with the balanced chemical equation where it's going to be 2 moles of butane is going to require 13 moles of oxygen, and it will produce 8 moles of carbon dioxide and 10 moles of water. So in the first situation here, we have 0.2 moles of butane gas and 2.6 moles of oxygen. Pause the video and try to determine which of those two will be the limiting reactant in this mixture. Okay, so we're going to start with 0.2 moles of butane gas, and then we're going to use the coefficients from the balanced chemical equation to see that for every 2 moles of butane gas consumed in the reaction, it's going to require 13 moles of oxygen gas. This means that the reaction will require 1.3 moles of oxygen gas to completely consume all the butane. So the butane will run out first since we have double that amount of oxygen gas present. So we will not run out of oxygen gas, we will run out of butane. Butane is our limiting reactant. Okay, for number 2 and 3, we're using the same balanced chemical equation but different reaction mixtures. Try to figure out what is the limiting reactant in both 2 and 3. I'll be back in a second to show you the answers. Okay, in the second reaction mixture, we're starting with 0.80 moles of butane, C4H10. We're going to use the same balanced chemical equation, so for every 2 moles of butane consumed, we're going to require 13 moles of oxygen. So this means that in order to consume all of the butane, I would need 5.2 moles of oxygen. I do not have 5.2 moles of oxygen, I only have 2 moles of oxygen. So I cannot completely consume the butane, which means that the oxygen gas must be the limiting reactant. That's going to stop the reaction. In question number 3, we're going to do the exact same process, but instead of mole to mole, we're going to do grams to grams. So we're going to start with 8.72 grams of butane, and then we're going to use the molar mass of butane to find out how many moles of butane that would be. Then we're going to use the balanced chemical equation to convert from moles of butane into moles of oxygen. And then we're going to use the molar mass of oxygen to find out how many grams of oxygen that would represent. But we're going to do it all as one big dimensional analysis problem that looks like this. After calculating the answer, we see that it would take 17.1 grams of O2 to completely consume all of the butane. Well, since we have 28.8 grams of O2, we have more than enough O2 to completely consume our butane. So the C4H10 butane, that is our limiting reactant. Now we're going to try to put it all together with some limiting and excess reactant stoichiometry problems. So in this first one, a student combines 65.5 grams of zinc with 1.3 moles of iodine in a synthesis reaction occurs. I want you to write the balanced chemical equation for the reaction. I want you to identify the limiting reactant, then calculate the theoretical yield in grams of the product of that synthesis reaction, and then calculate the mass of excess reactant left over after the reaction. Pause the video to give that a shot, and then I'll come back to show you the answer. So here's the balanced chemical equation for the reaction where solid zinc and solid iodine combine to form zinc iodide. Now remember, iodine as an element is diatomic, so the mole ratio is a 1:1:1 ratio. To determine the limiting reactant, we'll start with our 65.5 grams of zinc. We'll use the molar mass of zinc to convert to moles of zinc, and then the stoichiometric mole ratios to convert to moles of iodine to determine how many moles of iodine would be required to completely consume the zinc. Since it would require 1 mole of iodine to completely consume the zinc, and we have 1.3 moles of iodine present, that means that the zinc is going to be the limiting reactant. Now that I know that zinc is the limiting reactant, I can use that limiting reactant to determine how many grams of the synthesis product, the zinc iodide, will form. So I'm going to start with my 65.5 grams of zinc. I'm going to again convert that into moles of zinc by using the molar mass of zinc. And then I'm going to convert that from moles of zinc into moles of zinc iodine using the coefficients from the balanced chemical equation. In this case, it's 1:1, but in other reactions, it won't be 1:1, so we don't want to skip this step. And then lastly, to find the grams of this zinc iodide forming, I'm going to use the molar mass of zinc iodine to go from moles of zinc iodide
and I see that I'm going to have
grams of zinc iodide.
320 grams of zinc iodine forming.
This is called my theoretical yield. And lastly, now I want to calculate the mass of excess reactant left over. Well, I know from part B that iodine is my excess reactant, and I'll need to use 1.00 mole of it to completely consume the zinc. Now, since I started with 1.3 mole of iodine, and I'm going to use up 1.00 mole of iodine in the process, I find the difference and I'm going to have 0.3 mole of iodine excess. Now I can simply convert this into grams using the molar mass of iodine, and I'm going to find out the mass of excess reactant left over.
So we will have 76 grams of iodine remaining after the reaction has stopped.
If I wanted to, I could have done this entire process using a BCA table where I look at the moles of stuff before the reaction, the change during the reaction, and then what's left over after the reaction. Now looking at this BCA table, this has to be in moles. So I taught my 65.5 grams of zinc and quickly convert that into moles, and then list that before the reaction, I have 1 mole of zinc and 1.3 moles of iodine. Now since I know it's a 1:1 ratio, this makes it really easy to see that my zinc is going to be my limiting reactant because I need each of them in equal portions and I have more of the iodine. So I'm going to use up 1 mole of zinc in the reaction, and I'll use up 1 mole of iodine in the reaction. I'll have no zinc left over after the reaction. I'll have 0.3 moles of iodine left over after the reaction. Now, in the process of the reaction, we're going to form 1 mole of zinc iodine because, again, it's a 1 mole of the limiting reactant to 1 mole of the product ratio. So for every mole I use of the limiting reactant, I make a mole of the product. And then at the end of the reaction, I'll have 1 mole of my zinc iodine, which I can quickly convert into mass by using the molar mass of zinc iodide, which we found earlier to be 319.18 grams. Let's try another one of these problems where a student reacts 12.50 grams of solid copper with 0.35 moles of aqueous silver nitrate and a reaction occurs. Write the balanced chemical equation and then find the limiting reactant, the theoretical yield of solid product formed, and the moles of excess reactant left over. You can do this using a BCA table if you prefer, or dimensional analysis. I would recommend doing it both ways so you get good using both methods. I'm going to pause for a moment and you try the problem. I'll be right back. Okay, well let's look at this reaction. First off, we know that we're starting off with 12.50 grams of solid copper, but we need that to be converted into moles in order to use a BCA table. So we take the molar mass of copper, which is 63.55, and then we find out that that 12.50 grams of copper represents 0.197 mole of copper. The problem tells us that we have 0.350 moles of aqueous silver nitrate. And now we look at the mole ratios. It's a 1:2 ratio, so we need twice the amount of silver nitrate as we have copper in order to consume the copper. We do not have twice. We have less than twice the amount. So that means in this reaction, the silver nitrate will be the limiting reactant. But maybe that's not easy for you to see on your own. So let's look at the other method of finding the limiting reactant. If we're going to start with 12.5 grams of copper, we need to find out how much silver nitrate would be required to completely consume that. So we're going to go from grams of copper to mole of copper using the molar mass, and then mole of copper into mole of silver nitrate using the coefficients from the balanced chemical equation. We compute our answer and we find that it would require 0.393 moles of silver nitrate to completely consume all the copper. We do not have 0.393 moles, we only have 0.350 moles. So that means we're going to run out of silver nitrate before we completely consume the copper. Again, that means silver nitrate is our limiting reactant. Now, since silver nitrate is our limiting reactant, we know we're going to use all of the silver nitrate and we're going to have no silver nitrate left over after the reaction. We also know that the theoretical yield of our solid product, which in this case is silver metal, will be determined by the mole ratio between our limiting reactant and our product. Since that's a 2-to-2 ratio, that means we're going to use 0.350 mole of silver nitrate in the reaction, and we're going to produce 0.350 mole of silver as a product. I can quickly use the molar mass of silver of 107.87 to find that that means we're going to form 37.8 grams of silver. But again, maybe this BCA method is not for you. So let's look at the other way of determining the theoretical yield. It always starts with the limiting reactant, and we'll start with the amount of limiting reactant we have, which was said in the problem to be 0.350 mole of silver nitrate. We'll go from mole of silver nitrate into mole of our silver product using the balanced chemical equation of a 2-to-2 ratio, and then we'll use the molar mass of silver to find the mass of silver produced, which again would be 37.8 grams of silver. And lastly, we need to calculate the moles of excess reactant left over after the reaction. Well, if we're using the BCA table method, we know that it's a 2 moles of silver nitrate for every 1 mole of copper used in the reaction. So basically we use half the amount of copper as we're going to use for our silver nitrate. Since half of 0.350 is going to be 0.175 mole, that's how much copper is going to be consumed. At the start of the reaction, we had 0.197 mole of copper. We used up 0.175 mole of copper. So that means that after the reaction, we're going to have 0.022 mole of copper remaining. Again, we could do this with the dimensional analysis method, where we're going to take our moles of silver nitrate and find out how many moles of copper would be consumed in the reaction. Just like in the BCA table, we see that 0.175 mole needs to be consumed because there's a 2-to-1 ratio of silver nitrate to copper. But that's what's consumed in the reaction. So to find what's left over, we take our original amount that we started with, 0.197 mole of copper, we subtract out what we consumed in the reaction, 0.175 mole of copper, and then again we arrive at what's left over after the reaction, which is 0.022 mole of copper. Here's yet another problem for you to practice. I want you to try it out on your own and then go to the class website and check the answer key to see if you got it right.